Okay, so welcome to another lecture on topology. In this lecture, what we'll do is we'll relook at the definition of sequentially compact. We'll prove that the Lebesgue number lemma holds in a sequentially compact metric space. Okay, I should have mentioned metric space there. And then we will look at this result, which says that if you have a metric space, compactness, limit point compactness, and sequential compactness are all the same. They are all equivalent. So one implies the other if it's a metric space. If it is not a metric space, yes, we have seen examples of spaces which are what is that, limit point a limit point compact but not compact. We know that compactness implies limit point compactness. Okay, so yeah, so let's go ahead. So just to recall the definition, yeah, so we know what's a sequence. I don't have to go back over what's a sequence and subsequence, but a topological space X is said to be sequentially compact if every sequence of points in X has a convergent subsequence. If every sequence has a convergent subsequence, then we say that that topological space is sequentially compact. Yeah, now I won't give you examples here because the moment we prove the result that in a metric space compact is as good as sequentially compact, then in your usual Rn all your compact spaces will be examples of sequentially compact spaces. So you will have a lot of examples because in your metric spaces. So I will go next. So here is the lemma that we need to prove the next theorem. So the lemma is that if I have a metric space which is sequentially compact, then the Lebesgue number lemma holds in X. That is, there will exist a Lebesgue number. There exists, if you take an open cover, then it will have a Lebesgue number, some delta. So every open cover for X must have a Lebesgue number. That's what we need to prove. Okay, so the initial part of the proof, I won't do it separately. I will just go through it. I mean, it's to establish this thing over here. So the initial part of the theorem of this proof is to establish for every n we can choose a set Cn in X such that if diameter of Cn is less than 1 by n and Cn is not contained in the U alpha. So this is if we are going by contradiction. So suppose the Lebesgue number lemma does not hold for X. So we are taking a space X which is sequentially compact, and we want to prove Lebesgue number lemma holds. Suppose the Lebesgue number lemma does not hold. That means what? That means you have to have at least one open cover. So there exists one open cover which does not have a Lebesgue number. So there exists one open cover U alpha belong to J for X which does not have a Lebesgue number. It does not have a Lebesgue number means what? That means no matter what delta you choose, it cannot be a Lebesgue number, positive delta. That is, for every positive delta, there is some set of diameter less than delta which is not fully contained in U alpha. And this is not contained in any U alpha, that is U alpha for all alpha. So none of the U alphas contain this set. So, and that such a set should exist for every delta. So if you give me delta positive, if every set of diameter less than delta is contained in some U alpha, then this becomes the Lebesgue number. This we want to show Lebesgue number does not hold, that is at least one open cover does not have a Lebesgue number. So there exists a open cover which does not have a Lebesgue number. That means for all delta greater than 0, at least one set of diameter less than delta exists which is not contained in any of the U alphas. Okay, hence what I say is, hence for any natural number n we can choose a set Cn, meaning for every natural number n is as good as for every 1 by n positive. So for every delta positive something happens, well, that's going to hence happen for every 1 by n which is positive. So 1 by n's are all positive, so no matter what n you choose or no matter what 1 by n you take, we can find some set of diameter less than 1 by n. So there exists a set Cn whose diameter is less than 1 by n and Cn is not contained in any u alpha. So this particular statement here automatically implies this statement, where you just say, since we know this happens for all delta greater than 0, it will happen for all 1 by n which are greater than 0. Okay, so let me go now to actually prove this. I told you this part of the proof I don't want to repeat. So yeah, so we are proving that sequentially compact, then the Lebesgue number lemma holds. As I told you, we have assumed that suppose Lebesgue number does not hold, and we've arrived at this particular statement. We have hence been able to show this. Because the Lebesgue number lemma does not hold, we can draw the conclusion that this implies for every natural number n, we can choose a set Cn in X such that the diameter of Cn is less than 1 by n and Cn is not contained in any u alpha. Okay, now what we will do is we will now show that we can find a sequence which does not have a convergent subsequence. That is, now we are going to show that the space is not actually sequentially compact. So by contradiction, then we would have proved our result. So how do we construct this sequence which does not have a convergent sequence? So choose xn belonging to Cn for all n belonging to natural numbers. So by the way, we can choose a set Cn yeah, it's quite clear that since Cn is not contained in any u alpha, of course Cn cannot be empty. Not contained in u alpha means Cn is none. So each of the Cn's that we have are not contained in any u alpha. If Cn was empty, it would have been contained in u alpha. So that is obvious that Cn is non-empty. So we can choose xn belonging to Cn. So and this you do for all n belong to natural numbers. Now this particular sequence must have a convergent subsequence. So since X is sequentially compact, this implies xn has a convergent subsequence. So there exists subsequence, I will call it xni, which converges to some point. Let us just call that point A belonging to X. So there is some point in X to which this subsequence xni converges. Now this A is a point in X. Now A of course belongs to some u alpha A for some alpha A, I am calling it alpha A, for some alpha A belong to J. Okay, so A is a point in X, and since U alphas are covering the whole of X, every point should belong to one element of the cover. So there is some U alpha, you can see in the picture A belongs to some one particular U alpha. This implies now A is there in U alpha A, U alpha A is open. So what can you say? Hence it's an open set, therefore there exists ball around A of radius epsilon, which is fully contained inside U alpha A. That's because U alpha A is open. This is open. An open set and a point in the open set, and it's a metric space, so there is a ball around that point, which is, so you can see this is your ball around A of radius epsilon, this part. Okay, so now what we do is we have this we have already proved this claim for all natural numbers. We have something, so choose k large enough belonging to natural numbers large enough such that two things happen. One, 1 by nk is less than epsilon by 2. This we can obviously do because epsilon is positive. There is some ball around epsilon, or there exists epsilon ball which is fully contained inside U. So we have an epsilon. We have hence epsilon by 2, half of epsilon. Well, that's still a positive number, and you can choose k large enough such that your 1 by nk means your indices coming from the subsequence, right? There is a subsequence, there is xn1, xn2, xn3, xn4, and these keep increasing, n1, n2, n3, n4. At some stage n1 upon nk becomes less than epsilon by 2. So ensure that you are choosing k such that 1 upon nk is bigger than sorry, 1 upon nk less than epsilon by 2. Okay, and you can also ensure that you have chosen k large enough such that xnk belongs to ball around A of radius epsilon by 2. This of course is straightforward because your sequence xnk sorry, not xnk, xni, this sequence converges to A. So given any ball around A, you can choose k large enough such that after some point all points are in this ball, including xnk and beyond. Okay, so one can ensure that okay, so now what will we do? So now what we will do, ultimately we are trying to get some kind of a contradiction here, that we've assumed something that we want, I mean we want to show that the Lebesgue number lemma holds. We have assumed Lebesgue number lemma does not hold, and we want to get a contradiction, and the contradiction we are going to get is the following. This set CNK, remember the CNs are or the CIs are sets which are not contained in any U alphas. We are going to show that this CN is actually contained inside ball around A of radius epsilon, and we know ball around A of radius epsilon is fully inside U alpha A, right? Where is that? Ball around A of radius epsilon is fully inside U alpha A. So we can easily once we have shown that this CNK is inside this ball, it will be in U alpha. That will be a contradiction because CNs are not supposed to be contained in any U alpha. So yeah, that's my claim. In fact, I will write it. I claim that CNK is fully contained inside a ball around A of radius epsilon. In fact, you can write U alpha A because this is definitely inside U alpha A, but this is essentially what we want to prove. So take X, or let X belong to this set, we'll show it as in that set. Let X belong to C and K, right? You can see it in the picture also. X is in C and K. Then I want to show in this ball. If I have to show it's in this ball, then I have to look at the distance from X to A and show that this is less than epsilon. But this we know by triangle inequality. Look at the picture. By triangle inequality, this is less than equal to the distance from A to X and K plus the distance from X and K to X. X and K is in ball around A of radius epsilon by 2. So, A to X and K, definitely the distance is less than epsilon by 2, plus what about distance from X to X and K? Now, X belongs to this is, they are both in C and K. X and K is in C and K, and X also is taken in C and K. So, and the diameter of C and K, if you see on when we started out, the diameter of a CN is less than 1 by n. So, the diameter of your diameter of CNK will be less than NK. But sorry, no, is going to be CNK is CN is less than 1 by n, sorry. So, this will be, but 1 by NK is less than epsilon by 2. So, this here is less than epsilon by 2, because this distance is less than 1 by nk and 1 by nk is less than epsilon by 2. And what is that equal to? That is equal to epsilon. So, this implies your, if you take any point here, it is in ball around A of radius epsilon, but ball around A of radius epsilon is fully contained in U alpha A. So, this implies your C and K is fully inside U alpha A. But then that is a contradiction immediately, because your if you go up again, your Cn is not contained inside any U alpha, but here you have a Cn, in particular Cnk, which is contained inside U alpha A. So, that is a contradiction, and therefore, the Lebesgue number lemma holds in X. Okay, so that completes that particular proof. Okay, this is the next result that we need to do. I told you the second, there were 3 things to do. This is the theorem that I am going to prove now. Essentially meaning, if you have a metric space, then it does not matter. We have seen 3 notions of kind of compactness, whereas there is what we know as compactness. We know another notion of limit point compactness, which we saw is a weaker condition than compactness. That is, if a topological space is compact, it is limit point compact, but limit point compact does not imply compact. And then we have seen the notion of sequential compact space. In fact, it is if you go to the book, there are examples where you have a space which is compact but not sequentially compact, but not compact. So, that's there is no implication there, but in a metric space, the moment you take a metric space, all 3 are equivalent, meaning one implies the other. So, we will prove it. We will go by one the method of proof we will have is we will first prove 1 implies 2, 2 implies 3, and finally we will come to 3 implies 1. So, 1 implies 2. If X is compact, then X is limit point compact. Well, this has already been proved as theorem 28.1. We actually proved that, even forget metrizable, any topological space which is compact is automatically limit point compact. We have proved this. So, 1 implies 2, there is nothing to prove, or at least we have proved what needs to be done. Now, we go to X is limit point compact, then we have to show X is sequentially compact. So, let us do that. Okay, so not this. Okay, so yes, so that is what we will do. So, I will open a fresh page, and we need to prove that 2 implies 3, that is limit point compact, X is limit point compact, let's see. X is limit point compact implies X is sequentially compact. Okay, we need to show this. So let us assume that X is limit point compact. So let X be so you know what's limit point compact. If you have an infinite, if X has an infinite set, then it has a limit point. We want to show sequentially compact, so we have to show every sequence in X has a convergent subsequence. So yeah, so let Xn be a sequence in X, and I look at this set. Let A be the set of all the points Xn such that n belongs to natural numbers. So it's kind of the whatever is the sequence. Sometimes the sequence might have repeating points. For example, if the sequence is a constant sequence, then A has only one singleton point. So these are the points, the distinct points that are there in the sequence. We have two cases by which one is the obvious case, case 1 and case 2. So the first case, the easy case is if A is finite. The only way A can be finite is if there is one xn which is repeated infinitely many times, because if all the xn's, none of the xn's are repeated infinitely, if all the xn's are finite, then the total set of points that you will get xn n belong to all natural numbers would have been an infinite set. So the moment, because if none of the points of the sequence are repeated infinitely many times, because you have the there is x1, then there is x1, x2, x3, all these, and the sequence goes on. If all these points, if they are all, say there are two x1, then again there is there are two x1s and there are three x2s somewhere along the way. So in fact I should have just said the same points repeat, but only finitely many of them, then you still need infinite, because this total set is infinite. The natural numbers, the indices are infinite. So the only way you can get these points are just finite in number when you take them as points in X, is if at least one of them is repeated infinitely many times. So if A is finite, some xn has to be equal to some constant x for infinitely many n's. Values of n, let us say x is equal to xn1, which is the same as xn2 is the same as xn3, and so on. It goes on infinitely many of them. Well, you just take these infinitely many, where of course I am saying n1 less than n2 less than n3 and so on. So I have it infinitely many of these terms of the sequence are equal to x. Then you just take yn to be equal to yn or yi, whichever way you want, yi, to take this yi to be equal to x ni. Then this will give you a sequence, a subsequence of x, because it's exactly satisfying the definition of certain points. You are taking exactly those points which are equal to x, but then that this sequence yi is obviously going to converge to x, because it's the constant sequence. All the terms of that subsequence are constant, and so this is going to converge to x. So you are done. This sequence has a convergent subsequence. In case 1, if A is finite, then you are done. Case 2 is if A is infinite, then A will have a limit point, because we have assumed that X is limit point compact. So, if A is infinite, then let X naught equal to a limit point of A. Okay, and don't forget we are in a metric space. So, now what you can do is you can look at your space, and this is your X, and inside that you have your A. So, yeah, put right in red. So, there is an A here, and this set A has got a limit point x naught. So, there is a point x naught which is limit point of A. Now, what I will do is I will take ball around this x naught of all the radius radii 1 by n. So, there will be ball of radius, let us say take any of these balls. Now, x naught is the limit point of A. So, every one of these balls of radius, this is going to be your ball around x naught of radius 1 by n. All of these balls will have a point from A, and taking smaller and smaller such balls, I will be able to construct a sequence which actually converges to x naught. How do I do that? So, choose your choose let me say I want to construct a subsequence, right? So, yes, so choose x n1 belonging to A. Of course, keep in mind A has all, what is A? A has got all xn's. I mean, they might be repeating, but you can always, to start with, choose xn1 belong to A, intersection with ball around x naught of radius 1. Now, why should this ball have a point from A? Because x naught is a limit point of A. So, every ball around x naught should have a point from A. So, ball around x naught of radius 1 should have a point from A. That point from A will be some xn. So, take xn1, take that whatever it might be x5. So, then take x5 over there and call this as your y1. And having chosen y1 y2 equal to xn2 dot 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 yn yk equal to some x nk. So, having chosen certain, so I am going by induction kind of a step. So, first choose y1. Now, if you know y1, you can choose y2. And how do you choose the next one? Having up to some y, if you have chosen up to yk equal to xnk, then yk plus 1, you take this as some x n xnk plus 1 belonging to A intersection with or minus, I'll rather say A, from A you remove all the points y1 y2 up to the point y k, and then you intersect with ball around x naught of radius 1 upon k plus 1. Now you'll say, why should this ball around x naught of radius y k, 1 upon k plus 1 contain a point from this set? Well, we know it contains a point from A because it's a limit point of A, but why from this set? Well, we know in a metric space, if x naught is a limit point of A, then every neighborhood of x naught should contain infinitely many points of A. In fact, this happens in any T1 space, and any metric space is housed off. Forget T1, it's housed off. So this is definitely T1. So every neighborhood should have infinitely many points of A. So even from A, if you remove finitely many points, you still have to have some point of A in this ball, because this has infinitely many points of A. So still this intersection is non-empty, and you can choose a yk plus 1. So now what have you done? You have, hence it's obvious now that your yi is a subsequence oh, in fact, I have made a slight error. I have made a slight error. Yes, it is not y1, y2, yk, because otherwise that does not ensure subsequence. In fact, you have to take minus x1 up to xnk. I hope I have written it properly in the notes. Yes, I have done it properly there. So that's still a finite set, but this ensures that the next point that you take, the xnk plus 1 that you take, is even bigger than all of, so it's a bigger point. That is ensured by ensuring that it is taken bigger. This ensures that it is bigger than x, that xnk plus 1 is bigger than xnk. So yi is a subsequence of xn of this sequence. Why your sequence yn or yi is a subsequence of xn, and yi, this sequence will converge to x naught, because given, this is clear now, because given any neighborhood over here, have I proved it in the notes? Yeah, I have done it. Given any epsilon neighborhood of x naught, some 1 by n will be less, and then all terms of the sequence. I think you can just, it's quite obvious to see, and very often in metric spaces you must have done this construction. Once you have chosen your yi to be inside ball around x naught of radius 1 upon ki, then this sequence yi will definitely converge to x naught. It's there on page 78. Given any epsilon ball around this, it's very easy to see that this sequence converges. So again, even in case 2, we have found a convergent subsequence. So what we wanted to prove was that if x is limit point compact, then x is sequentially compact. To do that, to show it is sequentially compact, we started with a sequence xn. We have to show it has a convergent subsequence. In case 1, it was very easy because you had the constant sequence. In case 2 also, we have constructed a convergent subsequence. So we have ended up. Okay, so now what we will do is we will move on to the last part. So we have 1 implies 2, 2 implies 3 is done. Now we have to go to 3 implies 1. So yeah, we can take a fresh page and we are going to do 3 implies 1. That is to show that x is sequentially compact implies x is compact. So we have to take a open cover and show it as a finite subcover. But we will do it in 2 steps. We'll prove a claim first, and then we will do the main step. So here is the claim. Claim is that for every epsilon greater than 0, finitely many epsilon balls cover x. or there exists. What I'm rather saying is, the claim is, if you give me any epsilon, I can find finitely many epsilon balls that cover X. I'm not saying every collection of every finite collection is going to cover, but you can find one finite collection of epsilon balls that cover. So different points you will have to choose your epsilon balls to cover X. In fact, I think we have a picture for that, so we can pull that in on page 78. So 78.1, this should be the right picture. So this is exactly what we are saying, that there are different points you choose your epsilon balls, and finitely many of them are going to cover the whole of X. Suppose so I have to prove this claim. So yes, proof of this claim. Suppose otherwise. That is, no matter what finitely many you take, there is still some part of X which is left out. If that is the case, you can always take x1 belonging to any point in X, then choose x2 belonging to X minus ball around x1 of radius epsilon, choose x3 belonging to X minus ball around this is x1, ball around x1 of radius epsilon union ball around x2 of radius epsilon. Why is this non-empty? Because finitely many, we are assuming that this is not true. So no matter what finitely many balls you take of radius epsilon, some part of X should be left out, because it's not covering the whole of X. So this is non-empty, X minus this, so you can choose x3 there. In such a manner, you can choose your, in general, you can choose your xn belonging to X minus union I going from 1 to n ball around xi of radius epsilon. So ball around x1, x2 up to xn, you take all those n balls, they are still not covering the whole of X, because it's not covered by finitely many. So some point is left out, take xn to be one of those points which is left out, and so on. You keep doing this. So now you are going to have a sequence xn. You are immediately going to have this sequence xn. I claim that this sequence cannot have a convergent subsequence. In fact, this sequence has the property that look at this xn has property that if I choose, in fact, I'll just write it down, for any m mn belonging to natural numbers, m not equal to n, distance between xm and xn is greater than equal to epsilon. This sequence has the property, that is, this sequence is not a Cauchy sequence. Because if it was Cauchy, then given any epsilon, after some stage the distance between any 2 points is less than epsilon. But here I can say this. Why can I say this? Because if you give me any m n belong to natural numbers, one of them is smaller and they are not equal. So one is smaller, one is larger. So without loss of generality, you can always assume m is small, n is large. It doesn't matter, because one you are calling m and the other n. So think about it. At some stage you will have taken a x m, right, and then xm plus 1 up to, and then you are choosing your xn. And where do you choose xn? It is taken in X minus all these balls. So it is outside the ball around xm of radius epsilon, because from X you are removing all these balls. So what is the distance from xn to xm? Can it be less than epsilon? It definitely cannot be less than epsilon, because if it was less than epsilon, then xn would be in this ball. That means xn would be in one of these balls, but you removed all these balls from X while choosing xn. So xn has to be outside the ball around xm of radius epsilon. So the distance from xn to xm has to be greater than equal to epsilon. This implies this same property, that is for any this property, the one I am talking about is this property. For any epsilon, for any m n belong to natural numbers m not equal to n, the distance between xn and xm is greater than equal to epsilon. So this is for any term of the sequence. What you are saying is you have this sequence, right? x1, x2, x3, x4 and so on. Given any 2 points here, their distance is greater than equal to epsilon. Now what if you take a subsequence of this? Instead of taking all that points, suppose you take y1, then you take y2, then you take a y3. Well, the property is that if you take any 2 points, their distance is greater than equal to epsilon. Well, won't any subsequence also have the same property? Because they are the same points, and any two different points if you take, they are going to have the same property. Their distance is going to be greater than equal to epsilon. The same property holds for any subsequence of xn. So if this property holds for any subsequence, then that subsequence cannot converge, because in a metric space every convergent sequence has to be Cauchy. Of course, every Cauchy sequence need not converge, that is only if the metric space is complete, but definitely every convergent sequence has to be Cauchy. This implies for any subsequence, let me call it yn. So yn is not convergent. Why is it not convergent? Because it is not Cauchy. Every convergent sequence must be Cauchy. This is not Cauchy because this property shows that it is not Cauchy, hence it cannot be convergent. So this proves that this claim is true. For every epsilon greater than 0, finitely many epsilon balls cover X. Now actually doing the main part of the proof is very simple. Main part meaning now we have to show that it is the space X is compact. So let us take any open cover, let U alpha belong to J be any open cover. For X. So if you take any open cover for X, you want to show that this open cover has got a finite subcover. We have assumed the space is sequentially compact. So by previous lemma, every space that is sequentially compact, the Lebesgue number lemma holds. So by previous lemma, this cover has a Lebesgue number delta. So there is some Lebesgue number. That means if I take any set in X whose diameter is less than delta, it will be contained inside a U alpha. And I want to show that I want to cover it with epsilon balls, all of which are inside U alpha. So what should I take epsilon? What should I take epsilon, so that the diameter of this ball around x1 or any xn of radius epsilon, the diameter is less than delta? The answer to that question is you might think epsilon by 2 will work, but that will not work, because if I just take epsilon by 2, then the diameter is actually twice epsilon by 2, which is which would be equal to if I take this to be delta by 2, if I take epsilon to be delta by 2, then the diameter will be delta, but I want less than delta. So for that I have to come little less than epsilon by 2. So epsilon by 3 will work. So delta by 3. Take epsilon to be equal to delta by 3. The moment you take epsilon to be equal to delta by 3, then what is the diameter of ball around any point x of radius epsilon? This will be equal to twice epsilon, which will be in fact, you should not say this, it will be less than twice epsilon, that's less than or equal to twice epsilon, that I can guarantee that, because any 2 points their distance is going to be, by triangle inequality, given any 2 points their distance is from here to here plus from here to here, that's epsilon plus epsilon. So diameter is going to be less than or equal to twice epsilon, which is equal to, or which is strictly less than oh sorry, not less, strictly less than, this is equal to epsilon is equal to delta by 3. So this is equal to delta 2 by 3 delta, which is strictly less than delta, 2/3 of delta. So diameter of this epsilon ball is less than delta. This implies ball around x of radius epsilon is fully contained inside, in fact fully contained inside u alpha for all x belong to capital X. So if you take any ball around a point of radius epsilon, it will be inside some u alpha. So in particular what I can do is, I can say in particular, look at your we know that x is covered by finitely many. So x is covered by ball around some xi's of radius epsilon, this collection I going from 1 to n, some finitely many. So ball around x1 x2 up to some xm. Each one of these balls is contained inside a u alpha, and ball around xi of radius epsilon is contained inside some u alpha I going from 1 to dot dot up to n. Each one of them is contained inside some, this is because of the Lebesgue number lemma holding, and therefore this has diameter less than delta, so it is inside some u alpha. This implies, so these balls cover x and these balls are contained inside u alpha I, so definitely u alpha I going from 1 to n covers x, because the epsilon balls cover x and each epsilon ball is inside some u alpha. So when you take the unions of u alpha i's, I going from 1 to n, you are definitely taking all of these because they are inside them, and these itself cover, so this u alpha i's will cover, so this covers x. So we start, if we take an open cover for, what did we start with? We started with here, we started with let u alpha be an open cover for x, we have found a finite subcover. This implies that x is compact. So we have proved 3 implies 1. So we showed 1 implies 2, 2 implies 3, and then 3 implies 1. This completes the proof of this theorem. So yeah, we'll stop here, and the next lecture will be moving on to local compactness. Just like after doing connectedness we had done local connectedness, we will be looking at a notion of local compactness. So we'll continue in the next lecture.